Okay, good morning, everybody. Thank you very much for being here in person or by Zoom to this new Cerebral colloquium. We have today the pleasure to have with us today Professor Jürgen Blum. I'm very bad at German, sorry. He's a physicist at the Technische Universität in Braunschweig, in Lower Saxony, in Germany. Professor Blum studied physics and astronomy at Gießen and Heidelberg universities, and did his PhD at the Braunschweig Institute of Nuclear Physics in Heidelberg. And he did his habilitation at the Universität. He also spent 2 years at the Naval Research Laboratory in Washington, D.C., in the United States. His research, I hope this will be fun. His research explores the information of planets and comets. At the University's Institute of Geophysics and its University of Physics, he leads experimental and microgravity studies of dust aggregation, planetesimal information, and small body physics, integrating laboratory work with modeling and in collaboration for international space missions. Today, as you know, the colloquium is entitled The Long and Winding Road from Planetesimal to Comets. I thank again Professor Blum to accepting our invitation. It's a true honor for us to have you and the transfers.
Thank you very much. Thanks a lot for the kind invitation and for having me here. And thank you all for your attendance here, both online and in person. I'm very happy to talk to you about the long and winding road to planetesimals and to comets also. If you have no idea what planetesimals are, I'll tell you a little later. So this is all about how the first planetary bodies in the solar system formed and evolved into the contemporary bodies of the solar system. Should have forwarded, as it doesn't. Click on the screen. No. Here you go. Okay. I don't know how to get rid of that. Yeah. It vanished. Okay, so here is my introduction. And actually the result and the overview all together. So I'll run you through all these different phases. So from left to right proceeds time. So we start at t=0, whatever that is in the solar system. So some people believe it's the condensation of the first solid bodies. The disk, protoplanetary disk starts hot, and then it becomes colder as accretion rate drops, and then the first condensates form. That might reset the clock to t=0. So if you want to take that as a 0, it's fine. And then the first thing happens in a very short time scale, certainly shorter than 100,000 years. And then the disk phase goes along up to here, or I should point it to the online people as well. It's hard to see. So to the middle, it's the lifetime of the disk. It's a few million years, and then the gas is gone. And when there is dust, the dust will be gone along with the gas. So you better form large bodies in that time scale, so that when the gas goes away, the large bodies can still exist. And then the remainder of the time, obviously it's not linear, the remainder of the time until 4.6 gigayears after t=0, which is today, things also happen. And I will also briefly discuss those things. So let's start. Oh, it doesn't work. It worked before. Now, yeah, click in the screen. And you go out and you go out. Now, okay. First step is from dust grains to pebbles, which is what we're seeing here. And this is what I devoted most of my career, which has been going on a long time, as you can see from my age, studying exactly this process. So going from micron or submicron grains to whatever nature allows to form, which we in fact then term pebbles. It was said in the introduction that I performed lots of microgravity experiments. I will only show you one example here. If you have stereo eyes, you can watch both. If not, concentrate either on the left and right. That's the same movie from two different directions. What you're seeing here is aggregates that are in the bottom right picture here. Each aggregate initially is 100 microns or so in size. Each aggregate consists of what is in the center bottom shown of micron-sized silica particles, all the same size, nice. And then I start it all over again. So we start at a small collection of aggregates, shake up in vacuum under microgravity conditions, and watch what happens. The grains collide, the aggregates collide at typically speeds of about a few centimeters per second, which is what we think happens in protoplanetary disks as well. And in the end, after a few seconds of experimental time, you have this large, almost centimeter-sized aggregate formed. And we've done literally dozens of different types of such experiments and other experiments as well. And after many of those, and like 25 years of work, we ended up with a dust aggregate collision model, which is plotted in these 4 panels on the right-hand side. So the top, each panel shows the aggregate 1 as on the horizontal axis, the size of it, the aggregate number 2 on the vertical axis, and the top left panel is for micron-sized silica, the top right panel is for 100 nanometer-sized silica, the bottom left is for micron-sized water ice at 3 AU, and the bottom right is for water ice at 10 AU, because it matters where we are in the disk. Because as we go further out, the gas density becomes lower, gravity gets lower, things change, and that matters for the contours in the background. You see these dashed lines over here, which gives you in SI units, so in meters per second, the collision speed of each pair of particles. So if I just, because my arm is not long enough, point here at the bottom left, at about 1 centimeter vertical size, we have a 5 meter per second contour for everything that's 1 centimeter particle hits up to, again, 1 centimeter. Everything smaller than that is hit by this particular speed. And the colors in these plots show you what we think comes out when 2 aggregates of arbitrary size collide. Everything green or greenish means when they collide, there is a gain in mass. So either they completely stick together, so the mass kind of adds for both aggregates, or the larger one gains mass from the smaller one and grows. Everything that's yellow, that's bouncing, and everything that's red or reddish means reduction in mass. So things get smaller instead of growing. And I would like to point at this top right panel. At the bottom right corner, there is this what I call erosion barrier. So this is a very tiny phase space thing, but it determines everything in the end. This is what we call erosion, but this is just a scientific term for sandblasting. So as you see, it's on the bottom right. So there's one aggregate that is very large on the horizontal axis, and the other particle is very little. So it's small dust grain hitting a large aggregate. And as this is the case, the speeds here are super large, like 50 meters per second. So you hit a large dust aggregate continuously by small, bombarded by small particles, and it sandblasts away. It decreases in size. And if you, and we did once the exercise in this paper here on the bottom left plot, that we colored the whole thing green. So every collision artificially was made in order to hit and stick the particles, except for this bottom right corner, and of course it's symmetrical, the top left corner as well. And in the end, we could show here the biggest you can grow, even in this most optimistic scenario, is 10 centimeters in size. Nothing can grow larger than that. And there's other boundaries in that. So we've spent many years and millions of euros and tens of PhD and undergraduate theses on these things to come out with a set of papers which I think turned the expression of pebbles. You can see that here. So in these 2 papers, we did the first fully physical model of dust agglomeration. And in the second paper, there was a Monte Carlo simulation, how large aggregates can grow. And the largest aggregates can grow in the Schum et al. Paper on the top left. You can see that, for instance, for the MMSN, which is the minimal mass solar nebula model, you can grow centimeter particles of 1 gram in mass as a function of turbulence parameter, but that doesn't matter very much at most. This is the biggest you can physically, plausibly grow based on experiments and based on our understanding of how dust moves in protoplanetary disks and how protoplanetary disks are made up. This changes a little bit, as you can see in the middle plot here. If you go further away from 1 AU, that's the left plot, to into the Kuiper Belt region, 50 AU or so, then the largest aggregate mass decreases from roughly 1 gram to a milligram or so. So the size of these, what we term pebbles, decreases from a centimeter to a millimeter. And there's other works, more recent, that both confirms it or ends up with slightly smaller particles. But I strongly believe what we can physically understand that grows in protoplanetary disks due to mutual collisions and van der Waals acted sticking is centimeter to millimeter sizes. And this is what we call pebbles, and this is what everybody now calls pebbles. And this is also in pebble accretion, if you've ever heard of that. This is a mode of planet formation, which I will not be talking about today. Okay, is this all made up in a laboratory and numerically? No, this does have some counterpart in observations and with, of course, ALMA, and everybody here knows about ALMA much more than I do, probably. Protoplanetary disks like TW Hydrae here have been imaged, and if you have different wavelengths like ALMA has, you can infer from the different wavelengths and the appearance of the disk grain sizes. Of course, that needs a lot of modeling, whether the particles are extremely fluffy or compact. So there is uncertainties, certainly in order of magnitude in size uncertainties, but whatever you do, it turns out the typical sizes that you observe or infer from the observations in the inner parts of the disk, which are tens of AU for ALMA, are centimeters. And if you go further out to 50, 100 AU, we're in millimeters. So the same thing is observed, maybe slightly larger because we did that for 1 AU and 50 AU, and here's for 50 and 100. But typically, the observed sizes are also in the millimeter centimeter range, and even the best result is HL tau, as far as I know. And you see how model dependent it is on the right hand side. The two models that were used was a low porosity dust aggregate model and a high porosity dust aggregate model, and you can appreciate the difference here. However, all in all, we're seeing here centimeter is the canonical size. So if you hear of pebbles in the realm of protoplanetary disks, think about millimeter-sized aggregates consisting of micron or submicron-sized dust particles or ice particles wherever you are in the disk. Okay, so we have, in the first step, made pebbles. However, when I started my PhD, that was back in 1987. Most of you weren't born at the time, I guess. But my supervisor asked me to find out whether it is true that if you have a dust cloud in a protoplanetary disk, which we had not really observed at the time, that you can go to kilometer-sized planetesimals. Here's the term again. These are the smallest bodies that have enough inner gravity to dominate the remainder of the growth. So from kilometers onward, theoretically, the further growth is determined by gravity and not by van der Waals force as before. And I did my PhD work on the first experiment, and I found out, no, it is not working. And it was confirmed later by everything else. We end up at centimeters or millimeters. So how do we go to planetesimals? It took a long time to understand that. And the basics is here that we have individual pebbles which have centimeter sizes or millimeter to decimeter, whatever. And individually they cannot do anything because they're bouncing all the time. They're bouncing and they're drifting inwards. The drift inward is caused by the fact that a protoplanetary disk, which is consisting of 99% of gas and only 1% of dust, the gas is rotating subcapillary, slightly slower than capillary speed because there's a pressure gradient, radially inward directed pressure gradient, that lets the gas rotate by give or take 50 meters per second slower at 1 AU. And that means the particles feel friction with the gas, and that causes the pebbles to radially drift in. So you better act fast to turn the pebbles into something very big that is no longer dependent on the gas. Because if you don't, then all the pebbles fall into the central star, and no planets would ever fall. So people do hydrodynamics of protoplanetary disks, and I show you one, I think a very nice movie by Jake Simon. I stole this from his website. So we're looking onto the face of a protoplanetary disk in a co-rotating frame. So here is inward, here is outward. The length scale is the scale height, so we're looking at a very tiny piece. And what we're seeing here is a subcapillary rotating gas disk with pebbles inside. And the hydrodynamics of the pebbles and the interaction with the gas lead over time, I think I put it here and stop it, lead over time to density enhancements, spot-wise density enhancements that are up to a factor of 1,000 above the average density. So this is a super high enhancement. Why is that? Imagine you are a single pebble, you're riding on a single pebble along with a gas. You feel the friction, you're moving in. If you join with another pebble, you find a configuration that one pebble is behind the other pebble, that the first pebble feels the friction, and the pebble in the trailing does not feel the gas friction because it's shielded from the front pebble, and it pushes the front pebble all the time to become faster. So two pebbles together act slightly differently to a single pebble. So they catch up with the single pebble because they are slightly faster. They find a third pebble, and a fourth, and a fifth, and so on. A collection of pebbles becomes a stable configuration here. It's an instability, and it's an instability because it is a stable configuration. So a collection of pebbles decouples from the gas, collects all the pebbles on its path because the pebbles are slower, collects all the pebbles that are driven radially inward, and once it catches up with the mass density with the gas, so typically the mass density of the dust is 1% of that of the gas, but if the concentration is already has increased by a factor of 100, the density of the pebbles overcomes the density of the gas, and then the gas is sped up by the pebbles, and then the radial drift completely stops. And then it becomes a stable configuration. And this is without any gravity. This is a pure hydrodynamics. And this is an effect that was discovered only in 2005 by Jürgen and Goodman. And then later on, Anders Johansson in Heidelberg in his PhD thesis and collaborators, and this is again a movie by Jake Simon, showed that then at a certain concentration of the pebbles in this so-called streaming instability, gravity, the collective gravity of all the pebbles kicks in and forms a stable planetesimal. And this planetesimal has a canonical size of 100 kilometers. So it's huge. So you make the step from a centimeter pebble to, on the average, 100 kilometers within a few orbits. And that is the effect that was searched for a long time. So as of 2007, it was clear this might be a way to go and pursue. And from here, I would go on. So my conception of a planetesimal, here is a cometesimal, doesn't matter. A planetesimal is a collection of individual pebbles, brought together by streaming instability until the collective gravity holds the thing stable against any disturbance. Okay, so we form within a few orbits, so in no time, planetesimals. And immediately, if we form it, it matters how large the planetesimal is. I said the average is 100 kilometers. The largest are even 1,000 kilometers. The smallest are not known because the resolution of the simulations aren't sufficient yet. But there's no reason to not believe that kilometer-sized objects can also form. So I consider it such that this gravitational formation of a pebble cloud of planetesimals forms planetesimals of a size distribution from whatever the smallest might be, a kilometer, and the largest is 1,000 kilometers. So now it matters how large the aggregates are, whether they become a comet or not. And I wanted to talk about comets a little later. This is easily because this is my only equation I will be showing. The pressure inside, this is the central pressure, inside a gravitationally bound object of radius r, radius in kilometers, is 35 pascals times the radius in kilometers squared. For average sizes, of course, average density plays a little role, but not a dominant role. So we have 35 pascals in the center of a 1 kilometer body. We have 3,500 pascal in the center of a 10 kilometer body, and of course, you can do the math in your head. So we thought about what happens if we have such a pressure. So we produced pebble piles. So what you're seeing is a pebbles of 1 millimeter in the lab, exerted some pressure on the x-axis and measured the volume filling factor, the density. And you see it's a nice correlation between the density and the pressure. And on the next stage, this compression, then you see it's only on the bottom, on the right plot, you see it's only a few kilopascal. Again, a few kilopascal is a few kilometer in size. Increases the tensile strength, the inner cohesion of the pebbles, the van der Waals attraction of the pebbles, from give or take 1 pascal, if this is just a no gravitational bound object, it's 0 compression, to tens of pascal if it's an object of 10 kilometer or so in size. And from the modeling of cometary activity, we think we know that the higher the tensile strength, the less likely it is that this body becomes a comet, because gas pressure that drives out the dust or overcomes the cohesion almost never exceeds a few tens of pascals. And Nick actually knows all the details about that. So we think only the smallest bodies are so weakly bound pebble piles that they may become comets. So compaction matters here. Another thing that happens immediately after formation is the setting free of radioactive heat. So this is what I call thermal metamorphosis. So the point is, if we have a pebble pile like a comet, where the pebbles touch and are loosely bound, so with low cohesion, the heat conductivity is very little. As on the right-hand side plot, you can see as a function of temperature, the heat conductivity of a pebble pile. For 2 aggregate radii of 0.5 millimeter and 5 millimeters, so a millimeter pebble or a centimeter pebble. And if you remember from some physics class, the heat conductivity of normal matter, any matter that we daily work with, like glass or stone or something like that, typically is on the order of a few watts per Kelvin and meter. Here, the heat conductivity is thousands of that, or 10,000 even of that. So the heat conductivity of a pebble pile is extremely little, particularly if the temperature is low. If the temperature is high, then the radiative heat conductivity kicks in and then it becomes high. So what happens if you have a pebble pile and release energy? And the energy release is maybe due to radioactivity, which we all know from meteorite research. is present in the young solar system objects. We're not the only ones who've done that work. So Björn Davidsson has done a lot of work on that as well. And here you see different volatiles as they redistribute because of that heating inside in his case, a 35-kilometer radius planetesimal or cometesimal. And in our case, we have played with the formation time. So the earlier you form a body, the more radioactivity is still there. The later you form it, the less. And the size of the body. So we started at a 1 kilometer object body and ended up at a 40 kilometer object body. And the pie chart tells you which percentage of the volume gets to what temperature. And there's an example here in the bottom left plot for a 10 kilometer radius body formed 5 mega years after t equals 0. So some of the highly short-lived radioactive nuclei have already decayed a lot. And this is the internal redistribution of water. Originally, it was 0.1. So the internal has lost more than half of its water, and all the water has condensed in a very narrow, very shallow subsurface layer of highly enriched water. The enrichment is a factor of 4 or something like that. And this can be observed, and there is proof that this is observable, has been observed already in comets. So this might be an important point to remember. And some comets or cometesimals might be might have formed so early or might be large enough to even melt the ice. So melted ice is very unusual in celestial objects. On the surface, it's impossible because there's always vacuum, only for the Earth where there's an atmosphere. But inside an object where the vacuum is shielded by the dust around, the pebbles around, you can see happens if you have a pebble mixed of water ice and a refractory material. In this case, it was also silica. The water can melt and can destroy the pebbles, and it can lead to the collapse of the inner parts of the pebble pile. So this might completely restructure the internal makeup of a planetesimal. So the thermal metamorphosis might be absent, and then this is what is colored blue here. So the original makeup of all the volatiles and non-volatile materials might not change, or the other extreme, large planetesimals or planetesimals that are early and have inherited a lot of radioactive materials, they are devoid, this is the red color, of volatiles in the center, and they are enriched of volatiles in a shallow subsurface layer. This is the pictogram for it. And finally, so this acts over a few million years, and then the lifetime of the short-lived radioactive nuclei is over. And then the remainder of the time, the planetesimals are either stored in the what we today call the Kuiper belt, proto-Kuiper belt, or somewhere in the region of the giant planets, and then they may or may not undergo collisions. And that's the most tricky part because it's the least investigated part. What's happening? Again, we've done a laboratory experiment. This is microgravity, but in the lab we have a little drop tower in which we do this. Again, this is a pebble pile. Just to give you a range of sizes, this one in the experiment shown was 2 centimeters. So we go up to 5 centimeters or so in size, consisting of millimeter pebbles. We collide them at about 10 meters per second, and you see they're completely destroyed. So this happens if a loosely bound object, which is already a pebble pile, becomes a rubble pile in the end. So the pebbles are given back to the ambient environment, but the gas has already gone at the time. And then as dust in the solar system moves by radiative forces towards the central star, it is sooner or later lost. Okay, if we combine everything we know about collisions, which is admittedly not a lot, I think we can or should discriminate between collisions that are more or less harmless, which I call sub-catastrophic. On the other extreme are the super catastrophic collisions. So the collisions that are happening today in the asteroid belt are typically happening at 3 to 5 kilometers per second. This is really pretty fast. So collisions become very energetic. So the material is heated, all the volatiles evaporate, the material is compacted, it even melts. This is super catastrophic, and in between it is catastrophic. So the pebbles might survive, but the overall structure certainly will not survive. So if we combine everything, the gravitational compaction, the thermal metamorphosis, absent or present, and what we think we know about collisions, we can distinguish between 5 types of contemporary residues of the planetesimal era. So if we're very lucky, we find planetesimals that have never undergone catastrophic collisions or super catastrophic collisions, that were small enough or were formed so late that the heating was unimportant. They have their original structure, and the hope is that comets are close to that. However, they might be thermally metamorphosed. Who knows? If we see a comet, we're seeing the surface. We have no idea about the interior, or hardly any idea. Or the comet might also be a pebble pile. That might be. So it wasn't heated, but it was catastrophically reorganized. So pieces that are now here and there neighboring were not neighboring originally. Or they were not metamorphized and then catastrophically reorganized in rubble piles. Or if things are really bad, then everything was forgotten about the formation. Okay, the question is, can comets help us to identify this, or to identify stages of this planetesimal formation? And the first thing is that I strongly believe that comets do consist of pebbles. And I'll show you some of the evidence that I think we're having. So this is about astronomical observations. This is about meteor showers and about the results from the missions, particularly the Rosetta mission, of course, to comets 6 and 7P. When infrared astronomy had started with the IRIS satellite in the 1980s, I believe it was, the first picture of the all-sky infrared heavens showed there was streaks along the sky. And it turned out all the streaks were trails of material lost by comets. So comets do lose material. We know comets have tails and a coma. But what people most often don't know is that most of the matter that is released by a comet is in particles that are big enough not to be able to leave the orbit of the comet, only in the direction of the orbit, forward and backward. They might travel a little bit. And that leaves a streak on the sky, which is called a cometary trail. And this can be observed astronomically, and Richard Dahl in 2007 showed that the beta parameter, which is the ratio between the radiative pressure of the sun and the gravitational pressure of the sun, of these particles, is less than 10 to the minus 3, meaning they must be larger than millimeters in order to show this trail behavior. So infrared astronomy helped us to show that there we see the cometary orbits along the sky because the comet sheds large particles. And sometimes it happens that the Earth crosses one of these paths, and then we observe meteor showers. Yeah, you know, the Perseids and the Orionids, and there's many over the year. And people like Peter Jamieson have spent a lot of their time in characterizing the properties of the meteors we're seeing, particularly those from comets. And it's interesting, in this work a couple of years ago, Peter shows the meteor diameter from the observation of the impact one. When the meteor impacts the Earth's atmosphere, you get a meteor trail and you can determine the diameter. You see, this is typically a centimeter or so in size, matching perfectly, again, the pebble sizes we believe come from comets. And this is a cometary twin. So there is meteor evidence that comets shed centimeter particles. And the results from the Rosetta mission, we summarized that in the paper back in 2017. Here is the size, and these side bars that are like reddish or purplish in the middle show you the different instruments and their constraints on how large the dominating particles could be. And they all agree in this hatched region here, which is roughly has a radius of 5 millimeters or so, or a diameter of a centimeter. And if you don't believe that, I can show you one of the few images that the camera, Chiba camera on board the lander from Rosetta, the Philae lander, took. You may remember Rosetta's lander landed in the most unlikely position it could ever land in a crevice that only received half an hour of daylight in one revolution. So it hardly operated. So I think we have 5 images altogether, and one part of one of these images shows you what I think are the pebbles. And the people from the Chiba team analyzed the sizes. And the size distribution is such that typically they are centimeters or so. What you're seeing here might be the only images we are having from real pebbles. So voila. You believe that these are pebbles or don't, but the size matters. We know a lot about the composition. So surprising to me was that we have roughly 50-50 mixture of minerals. So we always thought comets are minerals and ices, but there seems to be lots of organic material. And one of the big surprises to me was even after a mission like Rosetta, which had cost $1 billion or several billion of euros, and had accompanied a comet very closely for over 2 years, we have absolutely no idea how much ice is in there. So the dust to ice ratio is basically unknown. It can be anything. Even if it is a single value or it has a distribution of values is unknown. So things that missions cannot answer are the things that people thought would be easy to answer in the beginning, in the planning of the mission. So that was one of the big surprises. One last thing is there is also some work that claims that the pebbles do have inner structure, like this fractal type of self-similar inner structure. And the reason of that is this inner structure leads to a model of the release of water vapor of a comet. Yeah, as I just said, we don't know how much ice is in there, but we know, of course, the ice as the comet comes closer to the sun will turn into vapor and will be evaporated. So this up and down scaling is a free parameter here. But the increase in water release as the comet approaches the perihelion and the decrease after the perihelion can be best modeled if the pebbles have inner structure. And I think Nick Attree here is working on a refinement of that model, and it is very, very complicated to model this steep increase. It is much steeper than the 1 over r squared that you would expect. You can see that. We decrease the distance to the sun by a factor of 3 and increase the intensity of the water release by a factor of 1,000 or so. This is really complex to explain. So maybe pebbles even have a structure. And if this is the case, then this tells us about the formation of the pebbles themselves, the different stages that we still have no idea about. Okay, so I conclude our knowledge about comets, particularly from the mission to Comet 67P, Churyumov-Gerasimenko, is that it seems to be that the comet is homogeneous down to the meter scale. And that would mean that Comet 67P at least does not have this differentiation in the ices, like in the pictogram, the second pictogram from the top here, because If the ice was concentrated in a shallow subsurface layer and the depth of that layer be larger than a few meters, it would have been noted by the concert instrument, so the radar instrument on board was set up. We know the comet is highly porous, so 75% porosity, give or take, which is automatically explained by the pebble model, because the pebble have internal porosity, the pebble packing has porosity, and if you do simple math, you end up at 75%. This makeup, as I showed you before, has automatically extremely low tensile strength. So if there was no large body as a parent body before comet 67P formed, so 67P is not a fragment of a larger body after a collision, then the tensile strength is on the order of 1 Pascal or even below, and that is in agreement with what people like Nick have found in the analysis of cliff collapses, for instance, on the comet, that the internal strength of the cometary material is sub-Pascal, which is unbelievably small. It is macrogranular, so many observations, radiometer data, the Shiva image, and many more have shown that it seems that the comet consists of things that have pebble sizes and the heat conductivity, which I showed you a calculation of, because it consists of pebbles and it's vacuum in between, seems also to be extremely low. So I've shown you pictures at low, the graph at low temperature, the heat conductivity is below 1,000 in watt per Kelvin a meter, and the only estimate is an upper limit of 9,000. So this is in a very nice agreement. And it does contain ices that have an extremely low melting point, so CO ice. Whether the CO ice is there intrinsically or bound into water ice or CO2 ice is not yet resolved, but this is something that people are still working. So my conclusion is the properties of cometary nuclei in general, because we know many cometary trails, we know many meteors from cometary trails, and we have one comet visited in detail. They can be readily explained by a two-stage formation process. We have initially dust. We know from observation of probabilities. They form pebbles. The pebbles may be concentrated in number densities such that the collective gravitational pull takes over, forms planetesimals. And if we're lucky and not too wrong with all our assumptions, then 67P is an example of the smallest form of planetesimals and not a fragment of a larger piece. This cannot be completely ruled out. So my conclusion is 67P is either the first top pictogram. So we have the fortunate case that we have a pristine planetesimal, or it is a rubble pile, pebble pile, the third here. This is certainly worth studying further in the future. So my conclusion, this was the conclusion about comets, my conclusion of the overall picture, it is very complicated to get from protoplanetarities to contemporary objects in the solar system. So the first stage is we turn the dust into pebbles, take away messages. Pebbles are this big, maybe millimeters, maybe 10 centimeters, on the order of that. Then there is some magic, hydrodynamics plus collective gravity that forms planetesimals. Not efficiently, about 50% efficiently, because the remainder of the pebbles are needed to form the terrestrial planets and the cores of the giant planets later on. This is what is called a pebble accretion. And then the processing starts with the planetesimals. If the planetesimals are very large, they certainly have enough radioactivity inherited to differentiate, and if they collide, to become very complex. If they are unlucky and end up in the asteroid belt, then the collision speeds are so high that the collisions are super super catastrophic, and then the only original planetesimals are those larger than 100 or a few hundred kilometers, so there's only a handful. But then they are so large that they are internally compacted and they don't tell us a lot about their formation. So we better, if we want to learn about the formation of planetesimals, we better find small bodies, either in the Kuiper belt or as comets when they come to us, or captured by astrogans or something like that. So the missions that are coming in the next years or decades will certainly help to improve our picture. So I hope I could show you it's complex, but it's doable. So for all the young people, I've worked now 35 years on that. It's worth it. So there's so many questions, don't take this as granted. So there's so many questions on the way. There's many riddles to be solved. And some may not be ever solved, I don't know. But the takeaway message is we've learned a lot in the past 35 years, both from, from all three things. Observations, I mean, the astronomy was revolutionary in the past decades. Then the computational power has intensified a lot. And also us laboratory people can help to solve some of the problems here. And we have, for the first time, something like a full picture, which still has, of course, open spots here and there, but we're doing our best to close those in the coming years. Thank you very much for your attention.
Thanks, Jürgen. It's a really nice overview of everything. Yeah, anyone have questions for me?
I solved everything.
Hello, guys. I'm not an expert in subject. Actually, I don't know nothing about this. I was wondering, what acts as a glue between these parts? Is it electric charge?
It is not, but it does have to do with electric charges. It's what we call van der Waals force. And the van der Waals force is a dipole interaction. So every atom is for a short period of time a dipole. So even the hydrogen atom has a nucleus and an electron. And the electron, of course, can be considered localized if you're not too deep into modern atomic physics. And so you have a dipole for a short moment, and this dipole induces a dipole at the neighboring atom, and that acts attractively. And this is what sums up to what we call the van der Waals force.
Okay, so this happens to covalent bands, right?
Yes.
Covalent.
Yeah.
Okay, I was wondering, actually, the reason of my question was, what if there's a metals there? Metals have a different kind of ties. In this case, we call metal ties. In this case, the dipole is not temporal, it's permanent, because at every collision, an electron or more can be extracted from the metal. My question is, does it matter whether there are many metals present? I mean, the metallicity plays a role or not?
Well, if you speak of metallicity, astrophysics is different. Metallicity is everything larger than helium, or more heavy than helium. Real metals, like conductors.
Yes, I meant real metals.
Yeah. I must admit, I've never investigated it because real metals are really rare initially in the condensates of the solar nebula. They form at a certain small temperature interval, so at a certain distance from the central star. But overall, Earth's metal was, which is a lot. I mean, Earth has a giant iron nickel core, but Earth's metal originally wasn't in pure metal, but in metal oxides, which are the first condensates to condense. Because the oxide have a condensation temperature of several thousand degrees and the metals are below that. So I don't believe the metals are extremely abundant originally, but if they were at some positions they may abundant or sometimes, I have absolutely no idea what that would mean to the collisions. I have not investigated that.
So in this sense, how do you see those meteors that form mainly by iron, for example?
Oh, those meteors are differentiated. So these are bodies
very rich in iron.
Yeah, but these are bodies like those, and those were meant for ISIS here. But if you have large planetesimals and form early, they get really hot inside. So the stones melt and differentiate into metals and lighter elements, and the metals sink to the center like in Earth. And if they undergo heavy collisions, they might release material from the core, which are then the metal meteorites. That does not mean that these metal cores were formed by metal dust that came together. This is a later process caused by the radioactive heating after a few million years.
Kind of evolutionary phenomenon.
It is evolutionary, yes. Certainly so.
Questions?
Hello. My question would go in the same direction. So most likely the original composition is phosphorid or something like that, isn't it? Would that make any difference in terms of the mechanism of aggregation and pebble formation? Because you have the metal there as an oxide, as you mentioned. Also, I was wondering, what is there any original role for organics? If you look at interplanetary dust particle, the organic content is like very intimately matched with the silicates and the rest of the composition. Is that original, or is that also a process, an evolutionary process?
I think some of the organics is certainly original, but the realm of the organic chemistry is so huge that nobody really has investigated this phase here, how you form pebbles from organic rich material, so that I cannot address that question. This has just not been investigated. This is something for the future. I'm aware of one work like 25 years ago from the Japanese team who has investigated what they thought at the time was a representative organic mixture. And they produced, I think, millimeter particles or centimeter particles and observed collisions. And they found it is heavily dependent on temperature for the organic material. It is not for the silicates. So it doesn't matter whether you are at 100 Kelvin or 500 Kelvin, the silicates behave all the same unless you are close to the melting temperature. For the organics, it matters a lot. If you are too cold, the organics become rock hard, and then they bounce off and don't stick. If you are too warm, they become kind of liquid, and they can be liquid even under vacuum conditions, because the vapor pressure is so low. And then they become very sticky. So it is extremely dependent on the actual composition of the organics, and I think nobody knows that, and the temperature. So there's two parameters that we have absolutely no handle about at the moment. But seeing the abundance of organic material in comet 67P, I would think this is an interesting thing to study in the future.
And another point is what about the shape of the monomers? Is there any evidence that they form as a spherical?
No, there is hardly any evidence that they form as spherical, but the evidence we're having is from meteorites. If you look at primitive meteorites, the carbonaceous comprises, they have the chondrules, which are molten things, doesn't matter here, and the meteorites called the matrix. And the matrix is the compacted dust, and there you can observe the individual dust particles. They are angular. However, we've done experiments in this phase here with spherical dust, with monodispersed dust, with angular dust, with a narrow size distribution and a wide size distribution. It doesn't change a lot. The behavior is very similar. So the actual shape of the monomer is second order importance here.
But you reckon that if there was any organics inside there, they could change the
If organics coated the surfaces, it might be very different, yes. But again, organics might be restricted to a narrow region in heliocentric distance. So too close to the sun, organics are gone or dehydrated, so they become carbon in the end. Too far away, they're covered by ice. So this might be interesting for the asteroid belt, maybe the core of Jupiter or so, but probably not further out and further in.
Yeah, thank you for the talk. I'm wondering whether the dynamics of the planetary disk can play a role, very particularly at the very beginning of the formation, whether there are tidal waves or density waves that can enhance.
Oh yeah, unfortunately they do. That complicates matters a lot. So there's lots of theoretical studies, numerical studies being done for the dynamics. Tidal waves are only important for disks that are heavy. So as long as the disk mass is below a tenth of a central star mass, the tidal waves are relatively unimportant, but hydrodynamics can be a beast. Certainly, turbulence is the buzzword here. Turbulence is decisive, but people more and more learn about the origin of turbulence, which might be magnetohydrodynamic in nature, and also about the quantity of turbulence. In the end, turbulence determines the accretion rate onto the star. This can be measured by the luminosity of young stars. So people get a handle on that, and it turns out this alpha parameter, which I showed in one of the plots at the beginning, is not super high. So they are not over turbulent. They are slightly turbulent, but this complicates matter because nothing is axisymmetric anymore, and hydrodynamics becomes very, very complicated. Yes, but many people work on that.
Yeah, I think if you saw Steve Dash's talk, you get Steve Dash was the visitor who gave program for Christmas. He talked a bit about turbulence and disks and and the planet and the bumps in the pressure of planets or gaps and things like that.
Yeah.
So I think there's a whole field for it.
Yes, and from the ALMA pictures we see, there is, of course, the dust is not evenly distributed, not even in the radial direction. And that might be due to larger bodies formed or snow lines or whatever. And there's many, many processes. It's really complex.
Great.
Thank you very much for this nice talk. I would like to comment that we have found evidence about some variability in the flux densities of some protoplanetary disks, taking advantage with the archives in the large interferometer. We compare the flux density in different epochs, and we have found some cases where in some protoplanetary disks, the flux decreased by a factor of 4 in a timeline of 20 years. And we try to relate this variability perhaps for the decrease of variability in the temperature, or try to relate with the changes in the luminosity of the central star, that there is no evidence. So I wonder if you have some idea to try to explain this variability in terms of perhaps collision, that fragment, the pebbles or millimeter grains, and now we are seeing only the small fragments that they are not able to emit in the ALMA bands, for example. I don't know if we have some reference or models to explain this phenomenon.
I fear I don't, but what you refer to is certainly very interesting. I think I saw some papers that have claimed the identification of protoplanets in ALMA pictures, and after a few years they were gone, where they should not be. And then the new interpretation was it was one of the rare catastrophic or super catastrophic collisions that releases a dust cloud. And the dust cloud, of course, disperses after a certain time, and then it's gone. So I think there is certainly we're at the stage where this can be discovered now and investigated in detail. But I think it needs more observations in the years to come, particularly with ALMA.
Found this in times of only 20 years, no? We
Yeah.
don't expect a very big variation in this short time scale.
Yes. Yeah, and they can only readily be explained by collisions, single events that may happen. Yeah. No, I don't think that any natural process other than collisions was inferred for explaining that. But I cannot refer to any paper out of my head.
Thanks. Any more questions?
Yeah. Thanks for the talk. It was very enlightening. I was wondering what kind of particles are those in rings? Regarding this classification of 5 types of piles, you have rings around Saturn, rings around Uranus, rings around dwarf planets in the trans-Neptunian region. I think that could be very enlightening as well.
I never thought about it. So all rings have in common that they're inside the Roche limit.
That's why there's a paper by Ne and Rubov.
There is one ring that is not. Yes. That is not in the Roche limit.
One ring?
Wow, yes.
It's
Wow, okay.
so this kind of classification could give us some clue about what's happening there, and a new way to find the Roche limit by considering the kind of pile.
Interesting. Okay, so inside the Roche limit, of course, it can be the breakup of some moon that became unstable in its orbit and wandered inside the Roche limit and then was destroyed. But with Quaoar, what do we know about that ring other than it's outside the Roche limit?
Occultations.
Yeah, I think I saw that. But what do we know about the particles that make up the ring? Do we know anything?
Millimeter size or centimeter size.
Okay. There is no direct observation other than the occultation.
No.
What a pity.
Still,
But the composition, you know, right?
the composition on Chariklos ring is almost modeled. Water ice and some silicates. Maybe it's an organic, but the center, Chariklos' center is closer than Quaoar. So the idea of why we have particles outside the Roche limit maybe is the assumptions on Roche limit.
I mean, because I would expect same kind of particles as in 67B.
And I wouldn't think that they were that related, really. I can say something about Saturn's rings, I don't know, John. But the Saturn's rings are 99.something% water ice.
Yeah, a Saturn, but in this
Yeah.
Neptunian region, you may have the same kind of particles as in 67B. And we have 12 rings for 67B. This would be a clue to discriminate both kinds and solving two problems at the same time.
So what you are trying to say, or what I understand, is that the Roche limit is a classical limit that assumes only gravity plays a role. If we have cohesion, but then the Roche limit walks towards the central object, right?
Yeah, maybe you assume mean densities of the particles.
Yeah.
And if you take out this assumption,
yes, then the Roche limit can be anywhere.
Yeah.
So they're sort of fractal particles, very low.
Or maybe fractal particles.
But I think they would be unlikely to be the kind of pristine things that formed in the protoplanetary disk. I would imagine these rings are from subsequent evolution from some of those things on the bottom. So I don't think they would be related. But maybe, as you said, maybe the physics of it could be similar.
So what is the assumption of Quaoar's density?
The body, central body.
Yeah. And then this density determines what the Roche limit is.
Yeah. Well, I need to check, but this is high enough. Is Quaoar is big enough.
It's big, yes. So it's compounded.
Yeah. So what happens if you destroy or you have a catastrophic, super catastrophic disruption of a original body with fractal particles outside?
Yeah.
And then you form a ring with these particles.
Yes.
With the original one.
Yeah.
So this is an excellent laboratory to check
That is true.
this kind of stuff.
Yeah. I need to check. Red ring. Yeah, might be interesting. Thank you very much for that suggestion. Okay, any more very quick questions? None online, I guess. Then, yeah, if there are no further questions, then we should wrap up. Let's thank Jürgen again for. We will go into the probably to the just the canteen and the other basic institute.